Okay. All right. So I got this from Data Bloom myself, and just going to use this to explain. So, darling, if you remember, we uh, did the 2D how to represent your vector in Python, and you can do it with just the maths. You can do it with just the raw code, or you can use functions. Functions or libraries in libraries is the right word. It's just they're just collection of functions that allow you to do separate different things. So like there are different libraries that you can just import and get separate functions in them to perform whatever you want to do, depending on what you want to do. And for mathematics and the numerical calculations, the main one we use is NumPy. So from this, what I have here, what we are doing is representing vector in Python using the normal Python syntax without any library, and this is and also doing it with with NumPy. NumPy is a Python library just to see the difference. So, and last week, what we did was mainly NumPy, but this one here is representing the vectors as a list over here, and it's basically it's almost the same thing. I also explained that the counting starts from 0, 1, and 2, and just like that. So it's almost the same thing. Then nothing really to say over here. So we also did vector addition, right? So yeah, easy stuff. Yeah. So you see, doing this with normal Python over here without any libraries, just the code. You see, you can. This is representing your vectors, vector v as which is 2 and 3, your x2 and your y3, vector w 2 and 1, right? And go ahead and do the addition. So when you want to add vectors, it adds element y. So x will add x, and y will add to y. So what we are doing here is just saying that multiply add v I plus w, so this plus this for v, and also multiply and also add this and do the same thing for the next component. So I is just like the range of vectors. So for this one, even if we increase the number of values over here, right, we make this one a 3D vector, it's just going to add it automatically, because we are for the code here, we are accommodating for an increase in the length. That's why the for function is here. So for any value of v and w, want to add it element wise, and then print the results as here z, right? And this is also another way to do it, which is the same as this, but then a different way. We're working more with this one instead of the zips. So that is easy to understand. So for I in the range of the length of V, so that this response, no matter the length of this, we are going to take the values in it, and then we are going to add them element wise for V and W, right? And then you get the output. So we did this one too, but we used NumPy. We used NumPy. We did it this way. We created an array. We created an array and stored the list here as a vector in the array. And what we did was just do v plus w. And because we called NumPy array, it's automatically going to understand that we want to add its element wise. So it's going to add this plus this, and all of that. And Richard is of the view that we should let you understand how you can do it. Like you can do it with the math, so that when you start using the libraries or the functions, it's easier. You know what the function is doing, so you can even create your own function to do something slightly different, because what the main thing that is np.array here has done is that it's allowing our code it's helping us eliminate all this, right? This was just making our code understand that I want you to add it one by one across all the values, right? And introducing the arrays here, then the NumPy function over here just eliminates all of that, and then you can just add the variables directly, and you get your output. Same thing. And I think we also do the scalar multiplication, right? Call the vector, give it a scalar as a constant, and multiply. And you know how it works. Once you know how it works with like with the math in paper, it's easier to replicate what you want to do, right? So we want to multiply 2 by 2 and 2 and minus 2 by 3. Right? That's what we want to do. So oh, do you want to, okay, I think Daniel just joined. Daniel, did you join last week? I think, yeah, I thought it was Dominic instead. So it was Daniel. Okay. So I'm just refreshing us on what we did last week and trying to complete what we were supposed to finish last week, and then we'll move on to this week's one. Hopefully, there'll be enough time to do that. Yeah. So, all right. So what we're doing here is we get the we define the constants we are using. It could be anything. You're using lambda here, so you get you understand that lambda is a constant, but it could actually be anything. It could be A, it could be B, it could be C, it could be anything. And then define the vector here, vector 2, 3. So this is supposed to be our results G. And what we want to do is that we want to multiply V times all the values in V. So we want to multiply lambda, the constant here, times all the values in V. So for x in the values of V. So that even if this increases, it's still going to multiply through, and not just the first two or the first three. Right. And with arrays it's simpler. It's just normal minus 2 times V, because already it knows that it's going to multiply through or. So that's the main difference. In lists, that's lists in Pythons, it doesn't allow you to work element wise. You have to call it manually. Either you call your whatever you want to work with out and work with it, or you define a function, or you call you do a loop that will loop through all the values and do the multiplication for you. But in the arrays, it's good. It understands as elements. Why? Is it said those? Daniel, please go on. Sorry.
Please, with regard to the vector, is it one row and one column, or is it one row and two columns?
Sorry, I don't think I don't think I go to you.
Okay. I'm saying, please, can you hear me?
Yeah, I can hear you.
Okay, please, with the vector that you define with np dot array,
Okay.
is it one row with two columns, or one row, one columns?
It's one row, two columns. I I don't know if I'm getting the explanation of the rows and columns well, but then columns
Yes.
are
Uh,
the y-axis, right? And rows are the x, right? Columns are the vertical ones, and rows are the horizontal ones, right? So for this one, x is x is 2 and y is 3. So it's two rows and one column. Yeah, two rows and one column. Is that what you mean? Is that what you want?
yes, yes, please.
Yeah.
Thank you.
Sorry. Okay. So two rows, one column. Yeah. And when with regards to that, it will be that will be when we are moving to matrix, right? This time we're just working with vectors. So so theoretically everything is just one column, right? When we get to matrix, it's going to be multiple columns, and then you can get like grades of data, right? So for now it's just one column, multiple rows, and the rows is what's going to help us define whether we are in a 2D space or a 3D space or whatever space we are in. The other side spaces and subspaces is supposed to be somewhere here. All right, so yeah, so that I was just trying to explain the difference between the array, doing the multiplication with the array and doing it with code. And for the code, there are different ways of writing. This is just one way. You could also do it in a different way, and some of them will be longer, some of them will just be shorter, some of them will have like will be more complicated than some, but it's the same thing that you're doing. So when you're trying to replicate the code mathematically, like code word for word, it's different, and you could get different kinds of code that will do the same thing for you. And but for the functions, they are sort of predefined. Once you call a function, there's a way to write it. You can't really modify it. So usually that one is it looks more similar. If you're working with libraries or functions, it's similar. If two different people use the same function, the syntax is sort of similar. But if they are supposed to do the same thing but like in just code, you get different options. That's why for most of the code like we have different ways of doing it. So for this one, you realize that there's an or here, which is a different way of calculating it, and this one is also a different way of doing the addition, and it's the same thing, but then yeah. Okay, so yeah, scalar multiplication, and the next thing was this is an exercise. Because of time, I wouldn't want you to do it, but maybe it will be in your assignment. I'll share the note with you so you can just refer to it and work with it. So yeah, please unmute yourself to stop me because I'm not in the tab right now. So if you raise your hand, I might not see. Okay, or if you send a text or anything, I might not see. So best thing is just to unmute yourself and just come in if you want to stop me at any point. All right, so this on the vector spaces, Richard explained most of these things like in class. So I'm trying not to do much talking on the explanation, but then vectors like represent the individual data points or features. Like in any data set, you have one column that's representing the feature is what's a vector is, right? The vector is representing that whole feature, that whole so like pixel intensities or sensor measurements or user ratings. And matrix is like the whole data set. And the main rules that govern how the vectors behave together is like that's like the axioms of vectors, right? And where these vectors live, like in quotes, live mathematically, and all of these like bring about the concept of vector spaces and and axioms, where they live and how they interact in layman terms. So think of vector space as a collection of objects, and along with two fundamental operations, that's the vector addition and the scalar multiplication. So for a collection to qualify as a vector space, these operations must satisfy a specific set of rules, and these rules are called the axioms. Okay, so they just ensure that the operations behave in a predictable or consistent way, and it helps you to group the vectors or separate them or tell you they are different or tell you they are same depending on whether they obey these rules that you give, right? And why am I defining why am I trying to give this definition? It just like allows you to, it just provides you like the solid foundation with the math, and once you know that our data vectors live in the vector space, we automatically know that they obey these kind of rules, and it allows you to build some techniques or some general techniques for data analysis and machine learning that will work consistently across a different type of data. Because once it's working with this kind of data, you know that to work with this kind of data because these and these are in the same vector space, right? So vector space is just the vector space and axioms just help you to classify vectors, understand that these and these vectors act like this and this act like this and this can be used to do this, and all of that. So that's what we're trying to do. So the main properties, I think it has like 10 axioms that must hold true. I think in this, okay, so 10, like there are about 10 axioms. The main ones, I think, commutative property, associative property, the distributive, scalar multiplication, scalar sum, and there's the existence of the additive inverse and all of that. So let's start with the commutative property. I'm going to explain what we have here. Yeah, okay, so we have vectors v, w, and t, right? It could be a, b, c, it could be anything. Just for whatever we are going to do here, we'll be using three vectors. So for commutative property, there is commutative property of addition, and the intuition is that no matter what order that you add the vectors, you should get the same results. So v plus u or u plus v should give you the same results, and that's what we're trying to do here. So we said that we created a new variable called commutative. So like what we're trying to do is that we want you to add the elements in v and w, right? And compare it and also add w plus v. So note the changes in the position. So v first plus w and w plus v. And if they are equal, I want you to tell me if, like, I want you to say true. So this is a Boolean operation, right? So Boolean operation is just true or false. So I pass this over here. This one, once I put the variable here in this form, before the this form, it's going to, the output is going to be either true or false, depending on whether it satisfies the condition I give in the variable. Okay, so for I in length, in this, for I in this, it's just making sure that it goes through all the values. If there's not there, it's just going to, might even get an error because you can't add lists together in Python. So this is making sure that I want you to add them element wise, okay, and compare it if you add it the other way around for the same, for the same range, and then tell me if it's true. Okay, so this is the commutative property. Do you guys understand? Okay, okay. I'm sorry, I'm rushing, but then please let me know if I'm going too fast or I'm not making sense at all. So I mean, it doesn't hurt. The main thing is for you to understand, not to rush through them. So if I'm rushing too much, please let me know. Okay. All right, so this is for the commutative property, and it could be written in a different way. The main idea of the code is that I'm trying to add this separately and see how it works. So if I created a NumPy array, it would have been way simpler because I won't need to include this line of code. I'll just do v plus w should be equal to w plus v, and then run it, and it's supposed to work for me, right? So that's one way to do it, and this is just there without any function. And also the additive inverse, the the additive inverse, it just simply means that every vector has an opposite vector that will cancel it out when you add it together. So once you add a vector to a corresponding vector, which is like to its opposite, to its inverse, you are supposed to get zero. That's the idea, right? So we take vector v, we negate it, that's the inverse of vector v, and add it element wise. That's what this is doing here, and then check if it corresponds. So as you can see, I'm getting 0 0, which means it corresponds. Right. Okay. And then this is the scalar distributive property. All of these are axioms that you can just use to confirm, or you can use it to check something else. Depending on what you want to check, you can use a particular axiom that will tell you that this works or this doesn't work. You don't have to necessarily run all 10 axioms to check if some vectors agree with each other. Okay. depending on what you want to do. We'll get to that. We'll get to that. So scalar distributive property, we have the distributive of a scalar sum, which is this significantly means that you just scale a vector by a sum of scalars. As when you scale a vector by a sum of scalars, the sum is the same as summing the vector scaled by each scalar individually. I don't know if I'm making sense. So let me see how I can explain it in a okay. So scaling a vector by a sum of scalars is the same as summing the vector scaled by each scalar individually. Okay, so we using the same this same vectors v and w, we can multiply by the scalars, and then the left side should be the same as the right side. So c plus d, when we add these scalars and multiply by, do you want to say something? Please go on. Just come in and talk. Yeah. Was that Daniel? Yeah.
Yes, please. For the scalar distribution property.
So sorry. Please
For the
speak up a
scalar
bit. Yeah.
distribution property,
Yeah.
come again.
Yeah. Please go on. I can hear
Okay.
you now.
Please, for the scalar distributive property,
Yeah.
it's from the property the formula that it was the scalar multiplying the vectors. But it seems that you are adding the scalars here multiplying by the vector.
Yeah. So
Actually, I do not get it here.
okay. 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 So it's just adding. Sorry. So scaling the vector by a sum of scalars should be the same as summing the vector scaled by each of the scalar individually. So what's so if you realize, we created two sides, like the left hand side and the right hand side, right? So c plus d, which is this scalars, when you add them and multiply it by your vector, it should be the same as you multiplying the scalars individually and adding it as you go on. Let me see if I can find the equation that I don't know if maybe the math will explain it better. Give me a second. I don't have the slides that he used here, but let me see if I can get the equation and explain it to you. Okay, I got something. Okay, let me know if you can see my screen. Yes. Okay, so this is our left hand side, this is our right hand side, right? So B and C are the scalars and A is the vector. Okay. So once you add the two scalars B and C and multiply it by your vector, you should get it should be the same as you multiplying B times your vector plus C times your vector. Okay, and that's the same, that's what I was trying to do over here. That's what I'm trying to do over here. So add the scalars and multiply it element wise, multiply it by the vector element wise, and also compare it to adding to multiplying it one by one, and then the left hand side should be equal to the right hand side. So it's let me see if I can. So c plus d mult sorry C plus D, all of that times our vector, which may be V, right, should be equal to C times the vector V alone plus D times the vector V alone. That is this clearer? Yeah, so this adding this and multiplying by the vector should be equal to as multiplying them separately and summing them. And that's the distributive over the scalars property. Distributive over scalar sum. Okay. And oh, this even that's it. This even is this is just for the commutative property option. Yeah. Okay. So let's say I want to let me explain with the NumPy ones with the NumPy. Yeah. So let me create a scalar C to be perhaps two, right? Sorry, three is fine too. So distributive scalar, right? Distributive scalar is essentially let me just so scalar will be equal to what we are trying to do is well say check if I multiply C, so I need two scalars over here. So okay, so C plus D, right, times vector V should be the same as C times vector V plus D times vector V. Right. I think best way is to let me just say A. This should be B. So I'll just alright. So let me get rid of this one. So print okay. So let's print A and print B. And let's see if you get the same thing. Run this run everything over again. So trying to run everything again. It's like let me refresh my page. Sorry. I'm having network issues. Okay. And run. Still refreshing. Okay, so run everything again and let's see. Where are you? Where are you? Where are you? Oh, I was trying to explain something. This is not part of this. Okay. Yes. All right. So see, A is the same as B, even though it's sort of the same, it's sort of different in terms of how it looks. And what we are trying to do, the distributive scalar is just to compare if this side is equal to this side, and once it agrees, it means it conforms with the axiom of distributive scalar sum. I don't know if this makes sense, Daniel.
Yes, yes, please. Thank you.
So that's the same thing that we're trying to do over here, but this one is without the library. This is just with code. So it's just the same thing. C plus D times the vector and doing this individually. All right. Let me run everything again so I get it. Okay. So I'll share the notebooks with you and then you can do these exercises. I'll separate them into an assignment so that you can just do it in a different notebook and submit that notebook. And yeah, and this is about the linear combinations. Did I skip spaces? Okay, yeah, I explained the spaces over here. So after the spaces, then we can talk about the linear combinations, right? So as I explained about how vectors represent the data points and the matrices are like the whole data set, we can combine vectors to create new ones, right? And this is like important to understand how vector spaces work, and that's what linear combination is all about. So a linear combination of sets of vectors is just any vector w or any vector. Okay, let me use this one. So a linear combination of vectors is formed by scaling some vectors and adding them together. So if you have vectors v and scalars c, then a linear combination is just going to be almost like a distributive sum of the vectors. So, right, multiply c1 v1 plus c2 v2 plus, so just like the distributive sum of the vectors. So in other words, we can create a new space, a new point in the data space by just stretching and adding the existing vectors, right? And yeah, so this is an example from the slides where we have vector I and vector j being multiplied by scalars 2 and 3, right? So let's do that over here. We first of all we define our vectors, which is what 1 and 0, right? So vector I is 1 and 0 and vector j is 0 and 1. So that's what we do over here. We define our vectors. And then we determine the coefficients or the constants that we'll be using. So alpha is 2, beta is 3. Just like here. It could be A, it could be C, it could be anything, right? Just for explanation and clarity. I'm just using alpha and beta over here. So it could be anything. So all doing this manually, all we are just trying to do is multiply what 2. So in this, let's do this over here first. So 2i is going to be 2 times 1 and 2 times 0, right? And that'll give us 2i. And 3j will be 3 times 0 and 3 times 1. So the scalar or the constant here is going to multiply all the elements in the vector. So that's what we are doing over here. Doing manually, what we are trying to do is say, hey, I want you to multiply alpha, which is 2, by the first element in I. So 0 is the first element in I. So 2 times this plus beta, which is 3, times the first element in J. Okay. And that will be my x value. That will be my first value in my new vector V. Okay, and then my second value in my vector V, I want you to multiply 2, which is alpha, by the second value, and beta here by the second value over here, right? So basically just this times this plus this times this, and then that'll be our first value, and then we go ahead and do the same 2 times this plus 3 times 1 and get our second value in that vector, and then this is the output that we got. I mean, it makes sense, right? So 2 times 1 plus 2 times 0, which will be 2, and then 3 times 0, which will give us 0, plus 3 times 1, which will be 3. And that's what we are doing over here, right? And the same thing using NumPy library, we have what NumPy arrays. We create our data set as an array, our vector, sorry, as an array, and do the same for j, and then create our variables. It could be this way, it could be this way, it's the same thing. So alpha is 2, beta is 3, and then we say alpha times I plus beta times j. And once we created it as an array, it knows that it's going to multiply it element wise, and then it does the addition for us, and we get our new vector here, right? And yeah, so that's how the linear combinations work. And this leads us to the concept of span. So the span of a set of vectors is just the set of all the possible linear combinations of the vectors. So it's just representing the entire original space that can be sort of reached or generated by combining these vectors. So there are about five rules of spans. Sorry, five types of spans. So we can have a span of a single non-zero vector, which is essentially a line through the origin, right? And we can have a span of two non-collinear vectors, which will so low-key span the entire 2D plane. We can have a span of two collinear vectors, which is a line through the origin, and that same line is defined by the vector alone. Okay, and we have a span of two non-collinear vectors in the 3D space, and we can also have the same span of three coplanar vectors, which is also in the 3D space. So the main thing is we can have a so what we usually work with, since we are working with a 2D space, will be a span of two non-collinear vectors, right? So let's review what we have here. A span of set of vectors is a set of all possible linear combinations you can form for them, right? So if you take all the combinations of this, which is you can get every vector in the 2D space because they span the entire 2D plane. So if you take these vectors and we try to find all the combinations of it, we can get. So how do we find all the combinations of it? You just have to give it a set of values. You can't necessarily find all because you can get infinite number of constants to multiply them by. So you just set a range from maybe from -2 to 3. Right, in the code here is -2 to 3 is the range we are working with. So we take this vector I and we multiply it by all the values in the range -2 to 3 and do same for g. And once you do that, see, these are all the possible combinations you get. And once you plot them on the num on the once you plot them on the graph, you're going to get something like this, right? So we're going to get all the points here. And you realize that if you trace all these points, it can pass through the origin. They all pass through the origin somehow. So this is over here. So this is a span of the x-axis and the y-axis. I mean, the vector is 1 0 and 0 1. So if x is 1, y is 0. So that's the x-axis essentially, and if x is 0, y is 1, that's the y-axis essentially. So a span of these lines that join each other, this is what you get, and this is like the standard values that I used to explain how spans work. So when I share the code with you, you get what's going on with the plots. The plots can be a bit tricky, but then once you read it, you just understand what's going on. All right. So this one was done with the math, right? We just did the math. We create a range and we multiply through, right? Like we use the same way we did a combination. So a times the first value of I plus b times the first value of j, and the second one will be a times the second value of I plus b times the second value of a. Just that this time a is not a constant value B is not a constant value, but it's a range. So it's going to take its unit wise. It's going to take minus 2 multiplied through minus 1 multiplied to, like that, till it gets to 2. And that's how we got all the combinations over here. Do the same thing for NumPy as well. Set a range, do the multiplication. It's almost the same thing, right? And yeah, and then you can get the span of these vectors. Any questions so far? Any question? Any question? We will finish this soon and go to this week's one. Health. Okay. So yeah, talk about linear independence of vectors, right? So it says that we can combine vectors using scalar multiplication and addition to form the linear combinations and expand, and these linear combinations will span a certain space or subspace. So a natural question that will arise is, if we give you a set of vectors that span a space, are all of them like truly necessary? Could the same span be achieved with, say, a fewer vectors because some are like repeating? And this brings the concept of linear independence. So if you realize, right, some of the values here can be gotten rid of, like this line, right? We move on to check the span of this. We realize that 0, 2, and 0, 1 are on the same line, right? They're on the same line. They are in the same direction. They're on the same line. So these are like redundant coordinates. They are repeating, and that makes 0, 2, and 0, 1 linearly dependent on each other. Okay, they are linearly dependent, and the explanation for linear, so I'll get there. I'll explain as we go. So I'm just trying to explain what I mean by linear dependence with this graph. And for 0, 2, and 1, 2, they are spanning the same space or subspace over here, but they are moving in different directions. Okay, so they are linearly independent. Okay, so that's like that's the layman's definition of these terms, the linear independence and linear independence. So mathematically, the way to check if your values, if you have two vectors that are linear independent, is to do a scalar distribution and equate it to zero. If you get a unit vector, it means they are independent, right? And another way, if you check the values that are on the same line, they are just multiples of each other. So 1, 1, and 2, 2, they are linearly dependent, and 1, 1 is just a multiple of 2, 2. So if you multiply this by 2, you get this. But for those that are independent, you cannot multiply, you can't scale them up to get them. I can't multiply any value by 1, 1 to get 1, 2. I can't, right? That means they are independent, right? So if you want to make sure that your value is linearly independent, this is the formula to use. So examples of linearly dependent vectors are vector 1, 2, and vector 2, 4 over here. So if you realize 1, 2 is just a multiple of 2, 4. If you plot them on a graph, you realize that they are on the same line. If you want them to pass through the origin, they'll pass through each other, right? And it just helps you get rid of repetitive features, or you can even use it to predict models. So once you have that's how most of the predictive models work. You have points, you have a lot of features, you're able to check that this and this have a certain, they are linearly dependent on each other. Then you know that how this vector will act, how this thing will act here. Once it gets here, it's going to, like, this is also going to have, it's going to have the same effects on this one. Able to predict how systems will react if you introduce something, because you know that they are on the same line, right? And they are moving the same direction. So yeah, so in simple words, if the only way to make this and this and this is zero to become zero, if the only way to make this scalar distribution to become zero is by choosing the constants to be 0, then these vectors are linearly independent, because it means that no vector can be formed using the others, and they are truly in different directions. Okay, but if there is at least one case that's when you make the constant 0, you are not getting 0, it means that they are linearly dependent. Okay, and they can be made from one another. Right. So that's what's is going on. That's what I'm trying to prove with the code over here. So we define two vectors. Vector 1 is 1 2, vector 2 is 2 4, and already we can tell that they are dependent because it's just 2 times v1 that will give me vector 2. Okay, so let's try to do the equation to see, to test if it will work. Okay, so you just get your constant c1 and c2 to be 2n minus 1, and then do the scalar multiplication or the scalar distribution, and we realize that, well, we get, once the result is a zero vector, it means that non-zero coefficients are found, so the vectors are linearly dependent on each other. So yeah, so in 2D space, if two vectors are linearly dependent, they are all lying on the same line which passes through the origin, and one is just a scaled version. When I say collinear, it's just a scaled version of the other, and the second vector does not expand the span of the line by that's defined by the first one. It's just on the same plane, right? But if the vectors are linearly independent, they are pointing in different directions and they are not collinear, and together they can span different parts of a 2D plane. Also, in 3D spaces, if the three vectors are linearly dependent, it means they line within the same plane that is passing through the origin, and at least one of the vectors can be expressed as a combination of the other two. And they cannot span the entire 3D space because they can just span one plane or a line. That's if they are all collinear. But if they are linearly independent, they point in different directions and they can span the 3D space. So that's the whole idea of linear codependency and all of that. Okay. So once you do the scalar multiplication and you get a zero vector, means they are linearly dependent. Okay. And that's about the linear dependency. I think the last thing is the, yeah, so all the all that's happening here is just trying to replicate the linear dependency with Python and with NumPy. I mean, it's still Python, but like one is without the functions, without libraries, and the other one is with libraries. So I'll share this notebook with you. Just go through. I don't want to explain because it's basically the same thing that I've explained over and over again. Okay, if you go through, you get it. Once you know how the equation looks like, you sort of get what's going on over here. Okay, and this one is exercise for you. I'll introduce it in the assignment, so you just be able to do it. Okay. Okay. So the last thing is the basis and dimensions, right? And I don't even know how to explain the basis for you to. But let's say you have a vector in a vector space. It's going to be termed as a basis for the vector space if it is linearly independent, right? So if the vectors in your subspace B are linearly independent, this means that no vector in the space can be, like as I explained with the linear independence. So if they are linearly independent, that means it can be a base of that vector. And if the set also spans a vector space V, that means it's also what's a vector space of the other. So an analogy that we can use to explain that is I'm trying to explain basis and also the change of basis, what it means, right? Let me read this right here. So a basis of a vector space, so V in this vector space R of n, is a set of linearly independent vectors that span the entire space. In other words, the basis gives us the directions we can move into reach any point in the space. So if the basis of V, so we have it here. So if it spans V, then it's a basis of V. And if the vectors are also linearly independent, then it's a basis of V. So if I give you two vectors, or I give you a vector, and I want you to check if it's a vector of, if it's a base of this vector, you have to check if they span each other, and you have to check if they are linearly independent. Okay, and yeah, yeah. So example is these two vectors over here from the standard basis that we used earlier. So this is I is just on the x-axis where y is 0, and j is on the y-axis where x is 0. So together they are like the Cartesian plane x, y, and y, right? So every vector here can be written as this. So the I and j is just the direction, right? So v1i plus v2j. This is the vector, right? The same thing. So any vector in R2 expresses V, and this one is, so we have vector I, vector j, and we have this vector, which can be any vector in this R2. So if you want to check if it's a base of this is what we do. So this is just setting them up. And now you try to, yeah, okay. So for example, right, with this I and j, they're like just east and north, right? X and Y. So if you have a vector that's V, 2, 3, or 3, 2, it just means that we are moving 2 units in the I direction and 2 units, sorry, so 2 and 3. So 2 units in the I direction and 3 units in the J direction. Okay. So let me use this analogy. Let's say you have, let's say you want to describe, you want to give directions to someone, right? Let's say you're in a city and you want to, like maybe you're in Accra, or yeah, you're in Accra and you want to give directions to someone. Depending on where you're standing, let's say someone wants to go to an imaginary place, right? You just give directions. In terms of this vector here, over here, 2 and 3, I'll like go 2 blocks east, go and take 2 steps, sorry, 3 steps forward, right? Or 3 steps north. So east and north are my reference directions, and that's my basis, right? And the numbers 2 and 3 are just telling me how far I have to go in each direction. So they are sort of like my coordinates. Okay, so that's the basis, right? It's just a set of reference directions that I can use to describe where the things are in space. Okay, so that's basis, right? So the change of basis has to do with your POV, right? Your perspective. So sometimes you can describe the same vector from a different perspective using a different basis. So let's say you want to go to the mall, Accra Mall. Yeah. If you ask me, I'll be like, you can get there coming from Medina. Once you alight over here, then you cross the bridge and you go here, and then you get to Accra Mall. So notice that Accra Mall will not change. There's a direct based on where you're coming from, and your direction will change, right? Yeah, that's an analogy to you. So let's say I you asked me for directions. I'm like 3 blocks east, 2 blocks north, right? And now you get a new map and it's been rotated. So your x-axis points somewhere else and your y-axis is pointing somewhere else. So if you want to describe the same location on this map, the numbers or the steps will change, even though the points that points in the space has not changed, but the coordinates will change. So you enter a class like where there's a desk there's a desk in the room. The desk is at the top right corner. Depending on where I'm standing, it might be at the top right corner, but depending on where someone is standing, it could be at the down left corner, right? The down left. Okay, so that's how the base work. But actually, the desk is at one place. It has not moved. But depending on where you are, it's going to change, right? So that's what the change of bases work. So you can describe the same vector from a different perspective using the different bases. And from the slide, I0, J0, right? So I is 10, J is 01, and the new base is this and this. Let this vector, once you multiply it, what will happen? You get it, you get the same coordinates but then different bases. So and that's what we're doing. So this is define the vector in the old bases, and we define the new bases vectors over here too. Okay, and then do the math over here. So v I divided by z, and then c1 is also this minus this, and it prints the new coordinates. Just lots of direction, but just for the same place. Right. So if you switch bases, they just have a new coordinates that will satisfy the same equation. Where the change of base matrix will just tell you how the new basis vectors are expressed in the old system. So it's like translating your measurements from one ruler orientation to another. So you have maybe you took measurements in inches and you're just trying to translate them into centimeters or something. It's the same length, but then the values will change. Okay. So the main thing to remember is that the vector itself will not change. It's the same thing in space. And what changes are the numbers that are using to describe it because you are using a different reference frame. Okay, it's like when you convert between Celsius and Fahrenheit or Celsius and Kelvin, the actual temperature is not changing, but the representation as the number is what's changing, and that's how change of basis works. Okay, yeah. So that's the end of this. The dimensions will come in the next one. So let me just touch on it. So the dimension of vector space equals to the number of vectors in its spaces. So for this, it needs two independent vectors. This is in a 2D space and it's in a 3D space. So it needs three independent vectors. Okay. So I'll share this notebook with you, and I'll give you a separate document for assignments. That will be based off this notebook, a couple of them, so that you just try your hands on them. And right, so we give you a new give you a vector and ask you to experience as a standard basis, and we give you the same vector and give you a new basis and ask you to express it in that basis. All right. Okay. So I think that's all for the first part of the class. I want to like sort of give you relevance of this in machine learning, right? So if you understand this concept of base and dimensions, it just it allows you to do something called feature space interpretation, where a set of all possible feature vectors in data sets is usually formed from a vector space. So the dimension of this space will correspond to the number of features, and then the number of independent features needed to describe the data. You can also do dimensionality reduction, and it helps you understand how complex a model is. So you can just use the input feature space to influence. You can tell how it's influenced the complexity required for machine learning model. That's the number of parameters in the linear model, right? You can use the dimensions to tell. Yeah, and yeah. So this is just application of this using vectors to predict the prices of house. Right. So maybe I'm trying to use this to move fast. And if you meet in the in if you meet one day, maybe Tuesday, if you meet on Tuesday, we can we can take up a project and break it down, instead of as we go down we'll be explaining what we are doing, so what we've been doing from the beginning to the end. Like to break it down and get a connection, okay, between the ML and all of that. Right. So let me. I created another notebook for this new one that we did what we'll be doing today, and we can also work with that one too and see. Please, do you guys have any questions in anything you want me to clarify before I start on this week's one? Hello, please go on, speak. Hello. So, any question? No, no question. Okay. Hope I didn't rush too much. And it's okay. Yeah, yeah.